Hi, welcome to our new series on basic mechanics, statics. This course will cover the Newtonian mechanics topics that are commonly found in an undergraduate engineering courses such as physics or of course a statics class. This course is the predecessor to a lot of fundamental courses in the field of engineering, whether you're a civil engineer or a mechanical engineer or any other type of engineer. Most of what we do in the physical world is tied to the contents that we'll be focused on in this class. So without further ado, let's get started. So this class is statics and will consist of a series of about 30 to 35 videos over the course of the semester. Now, as we stated in the intro, statics without a doubt is of fundamental importance. You have to understand the basics of what we're going to be doing in this particular class. Now, as we move forward in this class, a lot of courses require, in engineering in particular, require some sort of calculus background, or being able to do some heavy mathematics, governing differential equations or whatnot. This class is not that way. All right, we're going to focus mainly on the mathematics that can be solved with simple algebra, simple summations. There may be a little bit of simple integration, nothing more than a first or second degree integral, and nothing that requires the use of complex mathematical identities that you learned in your basic math classes. This is not a calculus class. All right, this is more how do I apply the rules that I learned in calculus to basically be able to do the steps. Statics, it forms the basis of everything that we do. So I'm a little biased when I talk about this class because obviously I'm teaching it, but to me it's the most important class that you as a college, generally a sophomore or second semester freshman, in engineering will need. This is the predecessor to courses like dynamics and mechanics and materials, which then become predecessors to classes such as machine mechanics or structural analysis or even fluid dynamics. All have their roots in what we're going to show you here. Now, there is a lot of mathematical overlap between this and topics that you'll see in a Calc 1 or Calc 2 class. We will be doing a lot with vectors, especially in the first 3 or 4 chapters of the book. This class will use the Beer and Johnson text as outlined in our syllabus, but for those of you that don't have a copy of that book, I'll provide the materials that you need here to at least understand the video. Now, if you're in my class, obviously you need the book to be able to do the homework, but for those of you that are watching this video online, you'll be able to get by with just with what I'm showing you here. The general format of what we're going to do is we're going to lay this thing out is basically I've got a series of notes, and I've been working on these notes for several years. This is about my 23rd time teaching statics, so I've done it a few times. I've also written a For Dummies book by Wiley called Statics for Dummies. You can see a link to that at the end of the credits of this video, as well as a For Dummies book for mechanics and materials. So I've got some experience in delivering content, hopefully, that will make this simple and easy to use. We'll start off with, like I say, some basic mechanics and understanding vectors and what the things that we can do with vectors. Don't worry if you've never seen a vector before, I'll outline the very basics of it. And in fact, I've been told that what we do with vectors in this class is actually help students who are in a Calc 2 or a Calc 3 class, either this semester or maybe in the coming semesters, that it's actually helped them understand better what's being presented to them from the pure math side of things. Engineers, by nature, we do things a little bit differently. All the rules still apply. We can't cheat the mathematics rules, but we do kind of look at things in a little bit different way than, say, the mathematicians or the physics faculty. So that's what we are. Now, statics is the study of bodies at rest. Okay, it all comes back down to Sir Isaac Newton and his 3 fundamental laws, and I've got those listed here. Isaac Newton obviously was a great mathematician and scientist from in the mid-1600s, born on Christmas Day, coincidentally, but he's probably most famous for his treatises on calculus, the Principia Mathematica, as well as the 3 fundamental laws of motion that we've all learned since even elementary school, we know what the laws are. We may not know what they mean, but everything that we do ties back to these three basic laws. If you recall, the first law, it says that bodies in motion tend to stay in motion, and that bodies at rest tend to stay at rest until they are acted on by an outside force. Okay, so that's the nature of what we're going to do. The second law is probably the most fundamental and popular equation, and I can't think of one that's probably more popular, and that's the old force equals mass times acceleration. Now, the notation that you'll see in this class, I'll do things a little bit differently because we're dealing with vectors. Anything that, so if I say F equals ma, that's what we learned, back in a high school physics class. I'm going to write this in a vector notation in which F is a vector if it has an arrow over the top, and then A is a vector over the arrow top. Now, what that does is it allows me to set up some relationships. It says if I have a vector on this side, I got to have one on the other side to be able to do the work. Anything without a vector, such as the case with this m, which would be the mass, is just a scalar quantity. And so a vector is an object that has magnitude and sense and direction and things like that. All right, now, this is the fundamental equation of motion, and it governs everything. In this class, though, we put a special restriction on this equation that this a vector has to be equal to 0, meaning that there is no acceleration. If there is no acceleration, the object, for our purposes, is considered to not have a force acting on it, or to not have some net force that will cause it to move. Now, obviously, in the situation of a constant velocity but with no acceleration, this may produce some challenges, but without getting into a whole lot of talk about viewports and scopes and scoping of problems and stuff, for what we're going to do, we'll take it as reference frames, I guess is the word I was trying to find on there, that we'll work on that. So that's our second law, force equals mass times acceleration. The third law says that for every force, it's the old force, there is an action. For every force of action, there is an equal and opposite reaction. Okay, and so that means that if I push on something, say I lean on a wall or something, the force I put into the wall, well, the wall is pushing back. Or if I'm standing on the ground, my weight is putting a force on the ground, and the ground is causing me is pushing back to hold me in place, i.e. that in a spatial sense, I'm not moving through space, that there's a balance that exists there. And if we can keep these three laws in mind, then we'll be in great shape as we start to move forward through the process. Okay, now, like I say, we talked about this force. The force has a direction and a magnitude. This is a vector. Okay, and so some examples of some very common vectors that we have weight vector. Okay, so if you remember that, that from your physics class, that we could define weight as simply being mass times gravity. So, well, if I put my vector notation, weight is a vector, and then mass is my scalar, and then g is my gravitational vector. Well, if you look, that's the same equation as what we have here. We just changed the letters on that. Okay. So g, now typically, this varies with location, where you're at on the planet Earth, or where you're at on any planet, or if the gravitational effect at that point is what determines the weight. Okay, and so for us, typically in this class, we're going to use either SI units or the English US customary units. Okay, for SI units, g will be taken as 9.81 meters per second squared, and English will be 32.2 feet per second squared will be our value here. Now, the thing that's interesting about this is that g has magnitude and direction. Okay, and if we kind of take it's kind of a quick and dirty example of this, let's just suppose that this is planet Earth. And here are my continents, not shaped like anything in particular, but if we think about, I'm a person standing at this point on the planet in the grand scheme of things, my weight, we know that gravity is acting down. But what if I'm standing over here on another side of the planet, like this? Well, now my weight is acting here. So that's my weight vector is always acting down relative to where I'm at. And this is where I said, it kind of, without getting into sense of the reference frames, now, that we would have an issue, like and so forth and so on, that all of these are my basic weight vector. Now, what's happening is that we know at the center of mass of the Earth, all of the g vectors are pointing in towards it. But if we think of this in math, absolute, in some sort of coordinate system that has x's and y's that looks something kind of like this, well, This guy would be a negative y direction vector. This guy is a positive y direction vector, and this would be a negative x, and of course if I had one over here, I'd get a positive x. Okay, so what happens is that by playing with vectors, I can track the direction of all these things just by playing with the signs that are associated with the gravitational constant. And in the coming videos, we'll show you how to set up these vectors using, Cartesian coordinate systems and different tricks for being able to do that. But once I have this, the vector equations for statics actually become very, very simple. Okay, but for otherwise, I've got a huge problem with just things acting in different directions, but they're still the same problem. It's the same person, just that it's a different location, and all based on my reference. So we'll play with things. This will be kind of our classic sign convention, and there'll be a lot of sign conventions that we'll start to talk with. But if I take this picture and I rotate it, now it's the same picture for this guy, and if I take it, now it's the same picture for this. And so by playing with vectors in these coordinate systems, I can start to look at these problems within the scope of this isolation box, if you will, or this reference frame, that everything is actually the same relative to that particular reference frame. And so we'll work on this. This will be a trick that you'll pick up in dynamics with rotating reference frames and those kind of things as well. But that's getting way down the track, putting the cart before the horse, so to say. So anyway, that's kind of what we have happening on that. Okay, all right. Now, so what we've done is just a simple example. We've got a mass of 1 kilogram, that the weight of this block is W is equal to mass times gravity, and then of course gravity is whatever the value is. So the units on this will tie directly into the units that come out of the force. Now mass obviously has its own set of units. In SI we're going to use kilograms, and in US customary units it's this strange unit called a slug. Okay, and we'll talk about the different units that you'll start to see. Okay, but all of those will factor into the units that we'll have for our particular weight. Okay, now the thing that's cool about vectors is vectors work for accelerations. They work for anything that has a magnitude and a direction. So things like displacement or things like velocity, anything can be measured that can be measured with those parameters can be represented as a vector, and then things will work very, very nicely in a compact mathematical sense as we start to kind of look at that. All right, so that's kind of where we're going. Now, some of the units that we're going to be using in this class, as we start to look, okay, some of the more common ones, time not so much, but that's okay because it's constant. It's the seconds are the base unit of time. But if we look at the length for the SI unit system, we're talking about the meter. Okay, for the US unit, we'll be talking about the feet. Okay, now we've got to be careful on this one, particularly with the US units, is that a lot of our measurements are often done in inches. Okay, and so sometimes there's a conversion of 12 inches per foot that has to happen on this. Okay, now in the front of your statics book, there's a table of common interpolation values that will allow you to change from one unit to the other that we can talk about. We talked about mass, the kilogram or kg. This uses the metric system where you've got your base unit of a gram, and then you've got your prefix, whether it's kilo or centi or deci. That's the one thing you got to kind of watch out for on those, but most of the problems we're going to cover we'll be dealing with kilograms. Okay, and then we've got the slug, which is actually a pound second squared per foot, is our unit for the basic slug. Okay, putting all this together, then the forces in the SI units, we're going to be talking about something called a Newton, which is basically a kilogram meter per second squared, or something like that, and then we're going to be talking about forces in terms of pounds when all this multiplies out. Okay, a couple of conversions. Again, most calculators will do this, or you may already know these values. I can switch between SI and metric. That we know that 1 foot is going to be equal to 0.3048 meters. 1 pound is 4.448 newtons, and then 1 slug is going to be 1 pound second squared per foot is equal to 14.59 kilograms. Okay, and of course that 1 inch is also 2.54 centimeters approximately. Now in this class we're going to be dealing with a lot of decimal values that things carry through. Now we can get into discussions of numerical accuracy and of precision and those kind of things. For the purposes of this class, we're going to, and if you're turning in homework or working a quiz or whatever, if you'll carry 3 decimal places under all circumstances, we'll get you close enough to the answers that are expected for the problems. Now again, I don't want to get bogged down in sensitivity of calculations. We're not doing anything with computers or anything like that. So our basic computations, we may not get the exact theoretical answer, but the methodology will show that it is sound, and then we can address those later as you get into more advanced classes and applied engineering mathematics or whatever the case may be. Okay, so we'll carry 2 to 3 decimal places pretty much in all circumstances. We don't want to round this guy up to 3.0 because that's a huge percent difference, but if I carry 2 decimals on him, he'll be all right. Okay, and so then, you know, other units that are in U.S. customary SI conversions, you can find those located in the Beer and Johnson table 1.3. We'll get you there. All right, so that kind of gets us kind of our setup for this basic introduction. All right, in the next video, we'll get into some basic vector equations and kind of some basic properties of vectors, and we'll start putting those to use for us. So stay tuned for that video. If this has helped you at all, give us a like or subscribe down below, and we will see you guys in the next video shortly. Thanks. Talk to you later. Bye.